Hello, this is Greg Marshall with MatSing. We're a technology company focused on RF lens applications. Basically, we create lens technology-enabled devices. We use RF lens technology to focus beams, which makes them tighter and cleaner without unwanted byproducts of side lobes, poor front-to-back ratios, and things of that nature. Lens technology-enabled devices can operate in a very broad frequency range. In this case, we did some testing at 2.4 gigahertz. So the testing that we did, I'll go through it, but let's start with the antenna that we used. We used the MS4H60 multi-beam lens antenna. It has 4 independent high-frequency cross-polarized beams, which will support 2x2 MIMO. The antenna has 0 to 15 degrees adjustable tilt. You can see the patterns below. There's 4 30-degree horizontal beams, and 30 degree, that's 10 dB down. That's not 3 dB down. If you look where the antennas, the beams on the antenna where they intercept, it's 10 dB down. You also look, there's very little overlap between adjacent beams. Overlap in this area would cause reduced throughput and poor coverage, so and reduction in capacity. So you can see the frequency range for this antenna is 1710 through 2690 megahertz. Basically, the antenna will support PCS, AWS, WCS, and yes, even 2.4 gigahertz Wi-Fi. So in this test we can break it apart into 2 separate things. First thing we did, we validated the pattern of the antenna utilizing an outdoor range. The second part of the testing was throughput at the seam between adjacent beams. We did this with non-co-channel and co-channel, loaded and non-loaded. Loaded meaning we had other UEs on the beams. We had one beam with one UE continuously transmitting files, while we had another UE on the other beam and continuously transmitting files, while the third device was transmitting files and measuring the throughput. So that's what loaded was. So let's go through and look at the test equipment used. Like I said, we used the MS4H60 antenna. We used 4 2.4 gigahertz access points. We used 3 smartphones with an FTP client application loaded on them, and also a Wi-Fi analyzer application. We had a laptop computer running FTP server. We had a Netgear PoE switch and an AC power inverter because we did not have power at the test facility. So here's a block diagram of the test configuration. On the right, you can see we have the antenna. There's 8 RF ports on that antenna, each one plus and minus 45 for each beam. So definitely worked very well for 2x2 MIMO. And what we did is we took the SSID on the access point. We named the one that was connected to beam 1 MatSing 1. The one that was connected to beam 2 we named MatSing 2. The access point that was connected to beam 3 we named MatSing 3, and then beam 4 SSID of MatSing 4. Each of these 4 access points was connected to a PoE switch which powered them and allowed transfer of data over Ethernet. We also had our FTP server connected to that switch, and we had 3 smartphones that accessed the 2.4 gigahertz Wi-Fi air interface to reach the antenna all the way through to the FTP server, and they were transferring files back and forth to that FTP server. Here's an aerial overview of the test facility. Here's the antenna, a picture of the antenna. It was only a 10-foot rad center. For this test, we just wanted to test in a simple environment. It's a big open field, but we were only up 10 feet. So here's the first test, pattern performance validation. Here's a layout of this test. So the blue dot in the center was where we actually had the antenna and the access points and the FTP server. And then the green dots around the arc, the perimeter there, with the blue circles around them, numbered 1 through 9, those are the actual test points. You can see we did it at the edge of the beam. Number 1 is at the edge of beam 1. Number 2 is right in the dominant server, right in the center of beam 1. 3 was the seam between beam 1 and 2. 4 was right in the middle of beam 2. 5 is seam between beam 2 and 3. 6 was right in the center of beam 3. 7 was the seam between beam 3 and beam 4. 8 was in the center of beam 4, and 9 was at the edge of beam 4. Let's go through these measurement points. Measurement point 1, this was near the outer edge. It was closer than the other data points. It was only 0.25 miles away, a quarter mile. You can see that beam 1, Matsing 1, was at neg 62 dBm. The next closest one was at the adjacent beam, beam 2, which was at neg 84, so 22 dB down. I think that's pretty impressive. Measurement point 2, this is beam 1, dominant server area, neg 63 dBm. Measurement point 3, seam between beams 1 and 2. You could see beams 1 and beam 2 are coming in at the same signal strength, neg 89, that's what we'd expect. Then measurement point 4 is beam 2's dominant server area, right in the center of beam 2. You can see the antenna, the white van in the background. We're at 0.36 miles away for this measurement point. And you could see beam 2 is coming in at neg 74. Beam 1 and beam 3, the adjacent beams, are significantly down, neg 91 and neg 96. Here's measurement point 5. This is at the seam between beams 2 and 3, and they're both coming in a dB apart from each other, neg 80, neg 81. Here's just a different screen on the Wi-Fi analyzer showing the information in a different format. Measurement point 6 is beam 3 dominant server area. Beam 3 is neg 72. Beam 1 and beam 2 are down 25 dB, significant. Here's another view on the Wi-Fi analyzer. Shows the link speed of 39 megabits per second. That's just the connection rate. This shows the channels that are used. So the seam between beams 3 and 4 is measurement point 7. They're coming within 2 dB of each other. Measurement point 8, dominant server area for beam 4. That's all we could see is beam 4 in that area, neg 73. And you can see measurement point 9 is a little up the hill from measurement point 8. So it can see further. In this case, beam 4 is neg 65. Everything else is significantly below it, but you can actually see the other beams from this location. So here's the results summary for the pattern performance validation testing we did. For each of the beam at the top, the table at the top, you can see the left column beam 1, 2, 3, 4. For each of those beams, we used non-overlapping channels with the exception of beam 1 and beam 4, which are farthest apart from each other. But Wi-Fi 2.4 gig offers 3 non-overlapping channels. If you use channel 1, 6, and 11, there's no overlap in the carriers. So what we did is we used channel 1 for beam 1, channel 6 for beam 2, channel 11 for beam 3, and then we used channel 1 again for beam 4. The table at the bottom shows each of the 9 measurement points, test locations, shows the distance from the location to the antenna, and actually put in there how much higher the antenna was above the measurement point device. Then we have RSSI and dBm, and then we show what beam the UE was connected to at the time we ran the throughput test. And you could see at the first test location, we had 13.94 megabits per second. And then it just lists what each of the beams RSSIs were coming in at. So neg 62, neg 84, neg 93, neg 98. So you can see obviously beam 1 very dominant. Test location 2, 20.46 megabits per second. That's right in the dominant server area of beam 1. Then measurement location 3 is the seam between beam 1 and beam 2, and you could see as this at the seams the throughput is significantly reduced. Measurement location 5 is also at a seam, and then measurement location 7 is at a seam. Okay, the second test that we did, this is throughput at the seams between adjacent beams. And what we did is we aligned the antenna so that the seam between beams 1 and beams 2 went down this road. And then we just took measurement points at various distances down that road away from the antenna. 1 being closest to the antenna, 5 being farthest. And it's hard to tell in this aerial view, but just after the 4th measurement point, there's a hill and it significantly drops off to the point where you can't even see the antenna at measurement point 5. So when we did the adjacent co-channel between beam 1 and beam 2, we had beam 1 on channel 6 and beam 2 on channel 6. The table below that shows test locations 1 through 5, and then off to the right, the darker blue is not loaded, and then the pinkish color is loaded. Not loaded means we only had a single Galaxy Samsung phone running FTP transmission, and there was nothing else on the network, nothing in the 2.4 gigahertz transmission. Everything was just the one device. When it was loaded, it meant that we had 2 UEs transferring files continuously on each of the beams, one on beam 1 and one on beam 2, and then the measurement device went in and actually measured the throughput while those devices were causing traffic. So it created a loaded environment. So the test results summary. There's 4 points here. The first point, the pattern performance validation testing shows that the seam between adjacent beams has slower throughput than when in the dominant server area, with UEs 1/3 of a mile from the antenna. This is true even when adjacent channels are not co-channel. A rad center of only 10 feet was utilized for this test. Higher rad center would produce larger footprint and even greater throughput. Point 2, significant throughput can be obtained at 1/3 of a mile in dominant server areas of beams. Test area had no external interference. If there were external interference, this could affect deployment results. Point 3, the lens antenna did a great job keeping dominant server far above the secondary or other transmissions from other beams, 20 to 30 dB in most cases. Point 4, adjacent beam seam testing showed significant degradation in throughput when the same frequency was used on both beams. This is even more apparent at greater distances and also when the channel is loaded by other UEs. Thank you for listening.